I must start by saying that this has been a very interesting meeting. I've been learning a lot. There have been lots of interesting talks. And my talk, I think it will overlap with some of the things that we have been hearing about these days. But I guess that's no problem. I guess I'll just try to reinforce some point, at least from our perspective. So I work in Acellera. Maybe I should start by presenting a bit who are we, who is Acellera. So we are a small company that was founded in 2006 in London. Right now, London is still the headquarters, but we are mainly in Barcelona right now. So the birth of Acellera has been cutting-edge technology applied to molecular simulation tools. And I'll talk a bit about this more in the future. So we are a small, medium enterprise. So we have a little above 10 people working, from developers, medchem, compchem. So we have a quite wide range of diversity in terms of people that are working in there, and also a very international team. I'm from Portugal. We have people from basically all around Europe, almost, working in the company, despite our small size. And we have been working mainly with the farm industry, but also some university research groups as well. Either through they are either our clients, or we even collaborate with them as well. Sometimes it really depends. So just a bit speaking also about the innovation. So ever since the foundation of Acellera, so one of the main products and the main boost for Acellera was ACMD simulation software, which was the first MD molecular dynamics software running on GPUs. Then after that, it was really a change in all the MD engines, because all of them now currently, or most of them, support already GPU. So it was really a game changer in that sense. Then in 2011, we showed the fitness of MD for drug discovery with this benzamidine trypsin study that was published in PNAS. I think it was. I wasn't at Acellera at that time. I think it was really like a groundbreaking paper. Then we also sold Metro Cubos, which are these workstations that are capable of. So they have lots of GPUs inside, normally 4, and they are normally sell them for this type of applications as well. Well, a bit similar to what NVIDIA also does with their DGX, or I don't know exactly the name right now. Then further along the line, we also been developing a bit the method. So adaptive sampling was something that was also very important to reduce the cost of MD simulations. For people that are aware of MD simulations, they know how much they cost computationally and how good improved sampling is. Then in 2015, we also released Ace Cloud, which was basically a way to run MD simulations on the cloud, basically through AWS. And it was basically, I think, at that time, very groundbreaking in that sense. So it was on the marketplace. People could just go there, use EC2 instances to run their MD simulations. It would be basically using it as a service. And yeah, it was very interesting. In 2016, this is when I joined Acellera. So HCMD, which is like a workflow pipeline, entire simulation platform entirely in Python, to do end-to-end simulations. So starting from the PDB, ending up in analysis of the results. So doing all the steps in between. I think it was also very revolutionizing. And recently, this is what I'm going to talk about. We launched PlayMolecule. So PlayMolecule. Actually, before I talk about PlayMolecule. PlayMolecule will be the focus, but let's a bit talk about what are we targeting at here. So everyone, or most of the people, know this, the drug discovery and development pipeline. So those numbers there, sometimes they vary, but they are good estimates of all the process, different phases that you have there. They take 12 to 15 years. They take a lot of money, all this process, and it's broken, right? Many people have said that this model is broken, and Acellera is trying to do its own part, helping mainly in those two areas, which is target analysis and validation, and screening hits to leads and lead optimization. So which mainly or sometimes are helped by computational tools. Our goals is to reduce cost and time, and also easy access and usage. This is very important to talk about here. Our expertise, as I said before, molecular dynamics simulations, computational chemistry, software development, medicinal chemists, more recently machine learning as well, and I will talk a bit about it, but we have many applications that use machine learning, but that won't be the focus of my talk. So what are the challenges? Because if we want to make these tools available for the people that are the end users, the medicinal chemists, what are the challenges for these people to use computational tools? And this has been like a kind of a brainstorm and some ideas that I present here. Usability. So this is one of the main issues. So graphical user interface, command line interface, an API. What is the best way to deliver these to the end user? Are the end users even know how to use an API, or they just want to click some buttons in their graphical user interface? This is very important, and there are different types of users, of course, but in the end, and especially for industrial applications, for pharma companies, people that want to deliver results, they want to focus on the science, they want to focus on discovering new molecules, they don't want to spend time reading your documentation, seeing how the hell am I going to do this? No, they want some easier solution, okay? Another important thing, which we've been talking about here a lot, about setup or installation, whatever you want to call it, which is how to correctly install and deploy complex tools and workflows. So also, the end user, the scientist, doesn't care much about this. Some people are curious, they maybe have some interest, but in general, they just want the tools to be correctly working.
Why did you put correctly there?
Yeah, correctly is important. Because that's the cornerstone, because if it's not correct, who cares? Also, another thing that is also very important here, which is infrastructure. So manage and use computational resources. Also, the medicinal chemists don't care if these jobs are going to run on the cloud, in their local cluster, whatever. They want their jobs to run. Wherever it is. They don't want to know what is the partition where you're running or how many CPUs you need. They don't care about that. This is a thing that we have been experiencing a lot. And also a final one, but I don't think this is especially more related with machine learning recently, which is the theory and method. Sometimes the medicinal chemists may not be experts on the methods behind the tools. This is also okay many times, especially for some of these more recent black box kind of methods, where they are very good, they are shown very good performances at predictions, but sometimes they are very low interpretability. Okay, so let's now talk a bit about PlayMolecule. So this is just a slide, an overview. So PlayMolecule, this is our vision for PlayMolecule. Redefining the drug discovery process and presenting an entire platform that has as much possible tools for the entire pipeline. So we also try to leverage state-of-the-art machine learning methods. We try to have human-machine graphical interface that allows the researchers also to take the final decisions. What I mean by this is try to take as much details as possible, but still allow the users to understand what they're doing and take decisions in the process. But the objective, of course, is to explore new targets, find new drugs, so they repurpose existing ones. So this is the final end of it. And of course, there are many different ways of providing this platform and supporting it in the company. So what is it so special about PlayMolecule is, well, we try to make basically it's a web-based platform for direct design based on MD and machine learning, and you can try it right now. I actually invite you guys if you want. I'll also do it a bit here. So this is visiting www.playmolecule.com. You can do it on your computer if you have internet available. So basically, the platform, this is a free version of the platform that anyone can use, okay? You can see here lots of tools and the pipeline, okay? You can also read our blog. You can explore the apps that are available. They are available in this kind of cards where we have some small explanations, how many jobs they run, all of them that have scientific publications attached to them. You can also consult their publications, okay? So there are different, many different tools available here, applications. So whenever I talk about applications, this is what I mean. These apps, okay? So it's basically a wrapper for a particular tool. So for example, if I'm interested, one of our so for example, if I'm interested in KDeep, for example, which maybe I did something wrong. Okay, maybe, okay. So basically it gives you an easy interface for you to interact with it, okay? You can do easily your inputs, you also have an app description, usage, so on and so forth. And one of the cornerstones of this is the graphical user interface. Most of the things have molecular visualization. So after you run something, for example, you have a job over there, okay? Some of the tools, they have 3D visualization. Actually, this one is only submitted. Anyway, just to give you a general feel of what's the then you can explore a bit more if you'd like. So moving on with the presentation. So the pipeline, this is just to give an overview of the things that we have already available and the different types of tasks that they can that they perform, the time that they take and what category they are. Okay, so we have been very active, and Acellera, we are not developing containers. We are not some of the presentations I've had here, it was people that are really developing these technologies. No, we are users of containers, and our focus is to develop applications for molecular medicine, okay? So how did containerization came to PlayMolecule? So in the beginning, there were very few applications in PlayMolecule in the initial development. So everything was smooth, okay. The host system was sufficient. There was no problems. The problem is that when the rapid increase of application demanded containerization, it was impossible, right? At a given point, when you develop a new application to put it there on your host, suddenly your NumPy version is no longer compatible with your previous application. And this was like a natural thing to occur. Containers came to us as the natural solution for this. And in the end, containerization has two roles in PlayMolecule. So there's the infrastructural role, where it allows us a better management of the backend, which is PlayMolecule Web Services. I'll talk to you a bit more about that. And there's also another role in the applications, which allows isolation, reproducibility, deployment, versioning, so on and so forth. This is just a very, very broad overview of I'm not giving here too many details. So in the end, the user can interact with the GUI server, right? Or actually, we also have it available. We have been testing it, some API to talk directly with the PlayMolecule Web Services. So this does all the raw job behind, where you can do some REST, you can do all these calls to it, okay? And basically this interacts with some databases, okay? I'm not going into the details of the backend. And then we also leverage computing, cloud computing, HPC, local clusters, okay? And this is done through containers, okay? And this is where the containers also play a role. Okay. Container technologies, which one to choose, right? I think we have been hearing a lot about this today, yesterday. I'm not going to advocate any solution. I'm going just to talk about a bit of how did we do it. So there are many options available. Some of them we have been talking about them in this meeting. Docker is definitely the most popular solution, for sure. But in the end, we went to Singularity. So Singularity, I must say that it's not only a question of HPC requiring, so It's not a question just being compatible for HPC. In many pharma companies, for example, where they have their own internal systems, they also require the same type of security. This is, I mean, Docker is amazing for systems that are virtualized, like you can run on AWS, whatever, doesn't matter, root permissions, who cares, right? But in these very well-defined systems, when you have to have user namespaces, user permissions, this is also very important. No, you have lots of security risks here. So Singularity came to us basically as a natural choice because it was accepted by our partners and customers. Okay, that's basically the main reason why. I'm not going to advocate here much more Singularity. The crucial features for us was this. So root privilege isolation, and for us in particular, GPU support, and I'll talk about it a bit later as well. Very important. I talked about AceMD, which is MD software running on GPU. Machine learning as well. We need GPUs. So, but there's a thing, it's still not as feature-rich as Docker, but I think it's getting there. Even Dave was talking about yesterday, Singularity CRI. I think that the steps are going there, and maybe in the future we can see Singularity as the most popular solution. We'll see. Okay, so I'm going to talk here about some of our problems. I think in the previous talk, someone talked, in this morning, someone talked about this, the dependency tree hell, right? So we have these people that work normally with us. So Acellera is a small company. We work together with UPF University. They have researchers that develop a lot of things in machine learning. So developers are not worried too much. They just want everything to work on their setting, and then it doesn't matter where it works again or if it works in the future. I'm sorry, it's being a bit honest here, but it's how it is. So, and then especially on when we are talking about this type of tools, this type of libraries, we'll see Python, right, which is everyone uses it, right? And then you have all these layers that build on top of it. IPython, NumPy, Numba, Cython, then you have Keras, PyTorch, TensorFlow, which Kenneth talked about it a lot in the morning. I think it was a very nice, interesting slide. So all of these, and after a while, what happens here is that all these tools, or most of them, they are heavily and actively developed, which means that they deprecate very fast. They have cross-dependency issues, like for example, some of these softwares then just work on the specific version of NumPy. I think this is familiar for many of you guys. So, and also drop support for older versions, deprecated software. So there are lots of things here that requires a lot of work of maintenance and trying to get all these stick together and work. So I think that here is where containers provide this isolation of having a working environment that is isolated from others. So I'm going to talk a bit about one of the things that I discussed a lot with my partners when they were developing recipes for building containers. So which I call the flexibility curse, right? So build recipes. They are generic, right? You can put anything there, right? So they give the developers total freedom and flexibility to build containers. You can build anything. It's freeform, right? But that flexibility, I think, in my opinion, comes with a curse. This is just taken from Singularity, a web page. I'm not saying that they advocate this type of practices. I'm just saying that it was an example, and I see it many times. So group install development tools. How will this behave in the future? Can it install its extra known packages? Git clone this OpenMPI. Which commits? New commits will break. I mean, and I see this, I'm not saying that, I see this happen all the time. All the time, people are not taking care that these things may not work. If I build in 10 minutes, or if I build again in 3 months, and I think these are very crucial and important features that bring to I think the main slide that I try to present, which is so building containers for the reproducibility. So one thing that I find it very important, I try to stress it all the time: maintenance. Test. I think this is obvious for everyone. Create good tests, unit tests, ways to test the container. So we already have the appropriate sections in the files to test the containers. I think that's very good. So there's also some challenges and some questions like update containers frequently or update when it's too late, right? Because containers are these very frozen things that we expect to work more in the future every time. But next time that a customer, someone else asks for a new feature for this, what are you going to do? Bootstrap your previous container? Or are you going to build it again? And then suddenly NumPy 1.10 does not work anymore. You know, so update containers frequently has been a bit my advocacy. I try to think that maintenance is very important. So I think that here there's still lots of work in this area. Then reproducibility. So enforcing structure into the build process. This is try to fight the curse of flexibility. Explicit version and build numbers. I'm going to give just one small example. Like you're building, getting from a Conda particular version from a particular version on Conda of a particular software version and build. But sometimes you think, okay, there was a version, then there was a new build out of it because the first one was wrong for some reason. But sometimes this is not true. Sometimes people just overwrite the same build. And this thing that you just installed 2 weeks ago does not work today anymore. This is just a warning of caution as well. I'll talk about it here, which is caching packages versus starting fresh. So we have been trying to also cache packages as much as possible, which allows us to circumvent these problems. But at a given point, it also causes other problems when we have cache. So it's like one of these, what we do, like is this short blanket, right? Where you try to cover from one side and it won't cover your feet, or you try to cover your feet, it's very hard to do. And I forgot about this. So limit human error is also important. I found yesterday CJ's talk when he was talking about HPC container maker. I think this is very interesting to have standards that limit the human error, that limits the amount of ways that we build, for example, OpenMPI. I don't know, 6 different flavors of it. No, we need to somewhat streamline and limit the amount of flexibility. Also another thing that is also important, which is, are we going to rely on dependency trees, the automatic dependencies that the program gives us? I'm talking, for example, in a Conda installation inside the container. Or are we going actually to save the environment, okay? Because the thing is, I install software X version 1.0 right now, which calls for all these 3 of dependencies with all particular versions. But if I install this software in 2 weeks, it will install more recent versions of the dependencies, and it may not work. So maybe you're interested in saving the actual environment, the entire software stack, the entire library stack, okay, and not just relying on Conda install your software of interest. So one thing that we have done was develop PM Builder, which is a Python library to structure container build. This is an internal library. I see here with EasyBuild, with the HPC Container Maker, that there are probably other solutions that you should look into. But this was very helpful for us to try to create some structure and help develop these applications. Because right now we have 15, but when we have 50, we need to have some structure across all of them so that we are not making mistakes along the way. Yeah, so we'll be trying the container maker from NVIDIA. So very important for us. So NVIDIA GPU support the --NV flag in Singularity. So this is essential for most of our applications. So our MD software runs on GPUs. Machine learning methods are much faster on GPUs, or some of them, they are essential. This, again, one thing that I won't talk too much about here is about performance. I must say that for our applications, for what we've been doing, we don't see much performance impact versus non-container. This is, but it's for our particular case. Maybe we'll face something else in the future. We also don't intend to scale. We don't use OpenMPI. We don't scale. We don't use much CPUs. Okay, most of our applications are focused on GPU, okay? So what we want is this very good interaction with the GPU, okay? It's something important. Then I have here my dreamland wish. So one of the things that it's very interesting is that since the drivers are at the kernel level, we cannot go around it, right? If I'm trying to deploy a particular version that uses a particular CUDA and I need a specific driver, as far as I know, as far as we know, it's not possible. It would be interesting, or it would be great if the technology could evolve so that you could also have the drivers, different drivers available for containers, so that I don't know, I can do whatever I want.